Hello, this is John Odi. In this part of the spin valve bench tutorial, we will begin by creating a new design from scratch and in the process discussing some detail, certain useful features of the software. Here is the state of our spin valve bench session from part 1 of this tutorial. Let us begin a new design from scratch. We go to the File menu and select New. The dialog box that assists with creating a new design is displayed. In the Templates box, let us select Empty Design. Click OK. Let us begin by giving our design a meaningful name. We click the root node and enter the new information here. Let us add our first component. To do this, we right-click the Design Components node and we click Add Normal Magnet. This creates a new normal magnetic component. This highlighted node is its sub-node. Here it is in the System View window. This is an array of single domain cells. The red arrows represent the magnetization vectors of the cells. Let us proceed and make some changes to its properties. We give it a more descriptive name. Let us make changes under the Geometry tab. The choice here, the Input Type box, determines how the main component dimensions we enter are to be interpreted. Let us enter some data. Notice that when I click away from the box, there is a slight delay as the design properties are updated. A packing factor different from 1 introduces spacing between the computational cells. Under the Materials tab, let us modify the angular dispersion of the magnetization vectors. Under the Display Options tab, let us modify some display attributes. We make a selection here to display computational cells. At the Views node, let us select the top view and let us click the Tight button to have the design fit completely in the display window. Let us take a look at what's on display. You can see that the sample is an array of separate cells. Next, let us pattern our sample into a custom shape. We will use the so-called Selida utility for this. Selida is a standalone array patterning utility that can be invoked from within MagOasis software products. A separate tutorial discusses Salida in detail. In Spinval Bench, we launch it from the Tools menu. Here we have Salida loading. It is completely loaded now. This box displays a geometric map of our sample that we can interact with. We will use a mask image to pattern our component. We select mask here. We click this button to select a mask file, mask file. There it is. We first reset the pattern by checking the clear box here and clicking All. We then apply the mask by clicking this button. There we have it. We conclude by transferring the shape to our Spinval Bench session by clicking the transfer button, this one. Let us close Salida. Here, back at Spinval Bench, we can see the pattern sample displayed. Let us display the front view. Let's click tight to make it all fit. So here is the device in the system view window. Through the Tools menu, we have access to other very useful utilities. These are MagOmat utility, MagJob utility. MagOmat allows the specification of local variations of magnetic anisotropy and initial magnetization directions for a sample. MagJob allows the submission, monitoring, and management of background calculation jobs. These are standalone utilities that can be invoked from within MagOasis software products. Separate tutorials discusses these utilities in detail. Electrical circuits are associated with Spinval Bench designs. Let us take a look at the one for this design. We click the electrical circuit node. We can see that a current in plane or CIP circuit is defined for the device. This circuit is fed by a constant current source. Let us display the circuit by checking this box. In the System View window, the electric circuit is now displayed here in blue. This is a current source. Let us click on the circuit to select it. Then let us use the mouse to move the handles to add clarity to the display. There. The current will flow from the source through the sample and flow around the rest of the circuit. These panels at the ends represent electrical input-output contacts. We can define custom electrical contact shapes for the sample. To do this, right-click the sample in the System View window and select Edit Electrical Contacts from the menu. The Electrical Contacts Editor is displayed. This box here is a special swatch for defining contact panels. Let us specify a different input contact. Making sure input is first selected here, we clear the contact by clicking the Reset Swatch button. Then using the mouse, we sweep out a new contact. Let us do the same thing for the output contact, which we first select here. Let us click OK. In the System View window, we can see the new electrical contacts defined for the sample. Back in the Control window, let us quickly add another component. This one will play the role of a permanent magnet bias. We add it at the Design Components node. Let us give it a meaningful name. Let us specify new geometric properties for it. Under the Material tab, let us make this a permanent magnet. And let's complete the orientation of its magnetization. Also, we want to exclude it from the device's electrical circuit. So let us uncheck this box. Back at the System View window, here is the current state of our design. Here is the PM bias component here. We are almost done with our design. Let us specify a new vector field that will be applied to the device and the output curves that will be generated during a calculation. Under the Applied Field node, we specify a new loop field. In the Output Curves category, in addition to the magnetization curve already selected, we specify a GMR transfer curve plot. Our design is now complete. Let us click the Run button to begin a calculation. As you can see, the calculation is now underway. Let us stop this calculation and instead load the exact same design already pre-calculated and recorded. There. We will continue looking at this design in part 3 of our tutorial series. With that, we come to the end of part 2 of the spin valve bench tutorial. Here is a recap of what we have learned and a preview of what's coming up in part 3. Thank you.